So it seems that we have a lot of duality between left and right derived functors. It would be really awesome if we had an adjunction, which encodes a lot of the assumptions from earlier. Let's quickly review some basic facts about adjuncts. They are a pair of functors, L and R, going back and forth from two categories. And we have a natural bijection on these Hom sets. So not only are these in bijection as sets, but the naturality means that given a morphism G from D2 to D1 in D, and F from C1 to C2 in C, the following is a commutative square. So the vertical maps are the only ones that are potentially ambiguous, and these are just the Hom functor applied. So take the left side, for example. The image of a function up to L from D1 to C1 is the map um, from LD2 to LD1 to C1 to C2. As notation suggests, we call L the the left adjoint, and R the right adjoint. So given morphisms from the Hom sets in bijection LD to C, we call the corresponding morphism D to RC its adjunct and express it like this. We call the map from D to RLD the adjunction unit, and the map LRC to C the adjunction co-unit. These are pretty cool. Notice that we can obtain all the other morphisms in the Hom sets in which these lie from them, i.e. factoring through them. That was pretty standard. It's time for some upgrades. We'd like to upgrade adjoint functors to model categories. A Quillen adjunction consisting of left and right Quillen functors is one that satisfies the following equivalent conditions. L preserves cofibrations and R preserves fibrations. L preserves acyclic cofibrations and R preserves acyclic fibrations. L preserves cofibrations and acyclic cofibrations, and R preserves fibrations and acyclic fibrations. The idea to keep in mind is that we want to associate L with preserving cofibrations and R with preserving fibrations. So let's check that those conditions are indeed all equivalent. Here are two observations that, if true, we could deduce all the previous conditions from. So a left adjoint preserves acyclic cofibrations precisely if its right adjoint preserves fibrations. Right, so intuitively we say R sends fibrations in C to fibrations in D. An acyclic cofibration in D would lift against this image, and somehow that means its image in C lifts against the original fibration. Dually, a left adjoint preserves cofibrations if its right adjoint preserves acyclic fibrations. We'll show statement 1 and 2 is again just dual, so let F be an acyclic cofibration in D and G a fibration in C. Then for every commutative diagram on the left, we have a corresponding commuting diagram on the right. By assumption, L preserves acyclic cofibrations, so there is a lift from LB to X on the right. We then apply the adjunction to get a lift on the left from B to Rx. Conversely, suppose R preserves fibrations. Then we have a lift on the left, which goes to a lift on the right by the same argument, and we are done. So let's keep seeing if and how Quillen adjunctions preserve model category structures. So given a Quillen adjunction, this lemma says that R of a path space object of X in C is a path space object in D for Rx if X was fibrant to begin with. Dually, if X was cofibrant to begin with, then its cylinder object is sent to a cylinder object for Lx under X. So we'll prove the second case. The first is dual. A neat property of adjoints is that right adjoints preserve limits and left adjoints preserve colimits. Hence, L of X disjoint union X is Lx disjoint union Lx. Well, then we can pull out the codiagonal map like so, observing that L preserves cofibrations. Well, since X is cofibrant, a map from X to Sil-X is an acyclic cofibration, and so Lx to L-Sil-X is also. Consider then the triangle L-Sil-X and Lx and another Lx. And by 2 out of 3 we see that L sil x to x is a weak equivalence, and we are done. And the properties of Quillen adjunctions go even deeper. On the level of homotopy categories, the derived functors of a Quillen adjunction are also adjoint functors. In the last video we showed that we could consider Hom sets in the homotopy category as Hom sets in the underlying category, so the adjunction condition is equivalently expressed as this. But we already have a bijection before modding out by homotopy classes by assumption, so it just remains to show that modding out by homotopy classes doesn't change anything. Which is to say, we want that if two maps Lx and Lx to y were homotopic, then their corresponding maps from x to ry are also homotopic, specifically left homotopic. Well, we showed that cylinder objects are sent to cylinder objects under L, so we can write a left homotopy from F to G in the following way. Well, then our adjunction gives us a corresponding left homotopy, and we're done. Quillen adjuncts can also strongly relate two model categories on the level of their homotopy categories. We say that there is a Quillen equivalence if any of the following equivalent conditions are met. First, the right-derived functor is an equivalence of categories. Second, if the left-derived functor is an equivalence of categories. Third, if for every cofibrant object D and D, the derived adjunction unit is a weak equivalence. So the first map in the composition here is the adjunction unit. The second is the fibrant replacement of LD. We call this composite the derived adjunction unit again. We also require the dual case, or I guess equivalently, that or sorry, not equivalently, we require both, that for every fibrant object, the following composite is a weak equivalence, where the first map is the cofibrant replacement of RC and the second is the adjunction co-unit. We call this composite the derived adjunction co-unit. Our fourth equivalent condition is that for each cofibrant object D and D, and every fibrant object C and C, a morphism D to RC is a weak equivalence if and only if its adjunct morphism LC to D is. So we definitely need to convince ourselves that all these conditions are indeed equivalent. 1 and 2 are easy to see that they're equivalent, so let's see how these are equivalent to 3. So a pair of adjoint functors is an equivalence of categories if and only if the adjunction unit and co-unit are natural isomorphisms. Hence it suffices to show that the adjunction unit and co-unit represent adjunction units and co-units in the homotopy category. So we will construct an adjunction co-unit and show that it is represented by a derived adjunction co-unit. We showed that this is the case for the adjunction unit and the other is dual. So again, we want to show that the derived adjunction unit is an adjunction unit in the homotopy category. So let D be in DC and consider the following commuting diagram from previous videos. So then I claim this shows these three things are isomorphic in the homotopy category. So the first and third follow just by commutativity. The middle one is the third, but with a fibrant replacement to PD, D to PD applied once more. Why is this isomorphic? Well, by assumption D is cofibrant, hence the map D to PD is an acyclic fibration, and left Quillen functors preserve those, so D to PD is a weak equivalence, hence an isomorphism in the homotopy category. Okay, we have an element in the homotopy category of D, so now we want to consider its adjunction unit and show that it is represented by a derived adjunction unit. Well, by definition, its adjunction unit is the image of the identity under this adjunction isomorphism. Well, LLPD is by what we just talked about, PLPD, which we showed is just PLD. On the right, we have our equivalent Hom set in regular C. So the adjunction unit is equivalently the image of the identity in this, so again, this is after the Hom functor. So it is a map from LD to PLD to PLD to PLD again, or simply just LD to PLD to PLD. Indeed, this is equivalently by adjunct properties this composite, which is a derived adjunction unit. Now we need to show that 3 and 4 are equivalent. To see that 4 implies 3, consider the weak equivalence Lx to PLx. So again, this is a weak equivalence by property of fibrant replacements. Then its LR adjunct is the following composite, which by assumption on 4 is a weak equivalence as well. But this is a derived unit, and since it is a weak equivalence, satisfies 3. Dually, we can show this for counits. Finally, let's see that 3 implies 4. So suppose LE to C is a weak equivalence, where D is cofibrant and C is fibrant. We want to show that its adjunct is a weak equivalence as well. Well, it fits into this commuting diagram. Notice that the bottom left is the composite derived adjunction unit, and we assumed by 3 that these were weak equivalences. The composite derived adjunction unit, F is a weak equivalence, so PF is by assumption. Well, R preserves acyclic fibrations, and since C is fibrant, we can use Kent-Brown's lemma to conclude that R preserves weak equivalences, so RPF and RJY are weak equivalences. So by 2 out of 3, the top composite adjunct is a weak equivalence as well. Our last result is thankfully a bit of a simplification. So given a Quillen adjunction, suppose R creates weak equivalences, by which we mean a morphism F in C is a weak equivalence precisely if RF is. Well, then we have a Quillen equivalence if and only if for all cofibrant objects D and D, the adjunction unit, not derived, is a weak equivalence. So let's prove this. Well, we just said that we have a Quillen equivalence if and only if for every cofibrant object the derived adjunction unit is a weak equivalence, and for every fibrant object the derived adjunction counit is a weak equivalence. Well, the derived adjunction unit had its first map as the map we are assuming in this proposition is a weak equivalence, and R preserves a second weak equivalence by assumption. Hence by 2 out of 3 we are done, conversely as well. So we only need to show this second condition is true, if and only if eta was a weak equivalence. Well, by assumption on R, the composite in 2 is a weak equivalence, if and only if it is after applying R. If we precompose this with this map by what we have just showed with regards to the first condition, this first map is a weak equivalence, so by 2 out of 3 the entire composite is a weak equivalence, if and only if the composite from before without precomposition was. Well, by the properties of adjuncts, look at the composite from condition 2, notice that this is its adjunct. The bottom map is a weak equivalence because of properties of cofibrant replacement, so assuming we have Quillen equivalence, then the top map becomes a weak equivalence. Conversely, if we assume the proposition, then the above map is by assumption a weak equivalence, and this implies the property that tells us we have a Quillen equivalence. I believe it was property 4.